Hello students. So we'll be starting the chapter that is chemical kinetics today. So this is our chapter that is chemical kinetics. So if you look at the syllabus here, the CBSE syllabus. So if we have here the rate of reactions, factor affecting rate of reactions, and order molecularity, rate law, specific rate constant, integrated rate equations, half-life, concept of collision theory, and activation energy and RNS equation. So this is our CBSE syllabus. Now, if I talk about today's lecture, so we will be seeing these things, that is the rate of a reaction, in which we will see two types of rate of reaction. The first one is the average rate of reaction, and the second one is instantaneous rate of reaction. Now, if you look at the topics for today, subtopics for today, so we will see what is a chemical reaction, and then we'll see that how chemical reaction is quantized by this kinetics. So we'll see an illustration of that. After that, we will see what is this rate of reaction. So this chapter is mainly about the rate. Okay, so we'll talk about how speed or how fast or how slow the reaction will be carried out. Then we will move to illustration of this rate of reaction, and we will see examples of rate of reaction. At last, we will see the types of rate of reaction. The first one is average rate of reaction, and second one is instantaneous rate of reaction. So let us start our today's class. The first thing is a chemical reaction. So whenever you see a chemical reaction, you want to characterize it. But to characterize it, we need to do two things. First of all, we need to see that whether reaction will happen or not. First thing, so that is decided by our thermodynamics. Second thing, we want to know that how fast or how slow that reaction will go on. So basically we are interested in its rate. Okay. So this is dealt by this chemical kinetics. So these two branches of chemistry deals with the feasibility of reaction plus the speed of reaction. Feasibility means whether the reaction will take place spontaneously or not. Spontaneously means we have to just initiate, or in some cases we do not have to initiate also. So once they are started, they are carried forward by themselves. We do not need any external factor constantly to drive the reaction. So in that case, we will say that okay, this reaction is feasible. So this is done with the help of thermodynamics. So we have studied in class 11th what is thermodynamics and how does it help to predict the feasibility of reaction. There we have seen the Gibbs-free energy that was saying that if the value of this Gibbs-free energy is negative, then we will say that okay, the reaction is feasible. Next point is the chemical kinetics. So what is chemical kinetics does? So chemical kinetics plays the role of predicting the rate of reaction, that how fast or how slow the reaction will go, right? So if you see the word chemical kinetics, so the word kinetics is derived from a Greek word which means kinesis, which means movement. Okay, so this word kinetics is derived from a Greek word kinesis, which means movement. Means the movement is kind of not a certain word very close to rate, but you can just associate this term, right? You can just associate this term with the speed of reaction. Sorry, it is not written rightly here. It will be KIN, kinetics. Next, if we see chemical kinetics, so what are the things that we'll be seeing in chemical kinetics? So it is a branch of chemical science that deals with the study of rates of chemical reaction first, and the factors that are affecting the reaction rate, like our concentration, like our temperature, like our pressure. Okay. So if I keep it in a nutshell, then I would say that our chemical reaction can be characterized by two things. Thermodynamics, checking the feasibility, that whether the reaction will occur spontaneously or not. And the second is the chemical kinetics, which decides that how fast or how slow the reaction will go. Now, in chemical kinetics, we do study about the rate of reaction first and the factor that affects that rate of reaction second, right? So this is our, main introductory part. Now, if you want to see an illustration of this, that what I have told till now, So we can take the example of conversion of this diamond into graphite. So it is a kind of reaction that goes very, very, very slow. Okay, so here is our conversion. So we know that diamond converts into graphite, but this process is very slow. You cannot observe with your naked eyes also, and it takes, I think, millions of years to convert this diamond into your graphite. Now thermodynamic data indicate that this reaction is feasible. First of all, it is feasible. Okay, very good, good enough. But I have told feasible. This reaction will happen spontaneously, but I have not mentioned any rate. So it is possible that this reaction may take a very long time. And just predicting that whether reaction will happen or not will not help in this case. Okay, so suppose the reaction takes place in a billion million of time, then the feasibility prediction is now out of no use. Now it is of no use. So you are saying that a reaction will happen in million or billion years. So for me or for you, that reaction will not be feasible in a sense. You can just think of it. Suppose a reaction is occurring in million or billion years, then for me or for you, that reaction will kind of non-spontaneous. It will seem to be non-spontaneous more appropriately. So to define that it is spontaneous, you have to also mention the rate so that the spontaneity can be justified. Okay. So this reaction is so slow that the change is not perceptible at all. Not perceptible means not visible, right? It is not visible at all. So this change is very slow. So here you can see that how we are using both thermodynamics and chemical kinetics to justify our view or our perspective. So we know that this diamond is not converted into graphite in very easy way. How we are predicting this? That yes, this conversion is happening. Okay, this is true. Spontaneously it is happening by thermodynamics. But since it is happening so slow, which is predicted by chemical kinetics, we cannot observe it. So both of our observations are you can say justified by thermodynamics plus chemical kinetics. So this is the reason that most people think that diamond is forever, because in their lifetime it is not possible that the diamond will completely convert into graphite, and it takes millions of years. So people think that it is not convertible to graphite, and once a diamond is always a diamond. Okay, so is this clear to all of you? Now let us move to what is the rate of reaction. So till now I have told you that this chemical kinetics tell about the rate of reaction, but how does this predict the rate of reaction? So we will see various law, our rate law, defining it more accurately. But for now, just give a brief introduction of what is this rate of reaction. So to consider the variability in the rate of reaction, so I have introduced right now you to a very slow reaction. Now some ionic reactions are very fast. Okay, very, very fast. For example, the precipitation of silver chloride occurs instantaneously by mixing aqueous solution of silver nitrate and sodium chloride. So what it is saying that if you take your silver nitrate and your sodium chloride, okay, and dissolve it in the water, now what will happen? This sodium will form nitrate and the silver will form chloride. So this first thing would happen. What would be the result of it? Since sodium chloride is not soluble in water, it is partially soluble in water, so it will quickly precipitate in the solution. And this, since it's an ionic reaction, it occurs very fastly, and it is a kind of double displacement reaction. So basically I am saying that we are having our AgNO3 and NaCl. Now as we are dissolving both of this in aqueous, you will quickly get your AgCl, which is precipitate plus NaNO3. Right? Is this clear to you? So this reaction is very faster. And how we can see that this reaction has occurred very fastly? By seeing the precipitate that is formed in aqueous solution. So by observing that precipitate, we can predict that, okay, this reaction is very fast. On the other hand, some reactions are very slow. The previous one we have seen was quite very slow. This conversion of diamond to graphite. We have one more, a quite fast reaction, but still a slow reaction, that is rusting of iron. Okay, this rusting of iron is not happening in days, or you can say weeks, but it happens in a month. You can say that if we introduce your ice or expose your iron to moisture for years, then it will start rusting. What is this rusting? It is basically an electrochemical reaction in which the iron is converted to your ferric oxide, that is Fe2O3. So this is conversion of Fe to Fe2O3, and some crystal of water is also present. Okay, so it is basically the conversion of iron into its oxide. It happens due to electrochemical reaction in which iron is oxidized to ferric oxide. Clear? Now both air and mixture of moisture are doing these things. Since the water is acting as your reducing agent, it is reducing this Fe. So this is the thing that is happening here. So this is also a very slow process. It is a spontaneous process. You know it very well. Just keep the iron in open. You will not have to apply any external heat or something, pressure like that, and it will occur spontaneously upon just contact with moisture. But this process is very slow, right? You will not just keep iron on Tuesday or on Wednesday. You will see the rusting. You will have to wait for months, or I would say years, to observe this rusting. And nowadays this rusting is also avoided by electroplating. So that's a different matter of electrochemistry. Okay, so this is done. Now there are reactions like inversion of sugar and the hydrolysis of starch, which proceed with a moderate speed. So inversion of sugarcane, you will see this about this reaction kinetics more closely in the coming slides. But assume that for now, that is hydrolysis of starch and this inversion of sugar, this both proceed with moderate speed. Now, why is this rate of reaction different for different thing? Basically, this kinetics is the study of that. So we have seen a variety of reaction, a variability in their speed, starting from ionic reaction, which happen instantly in a minute, in a blink of eye. Then we have seen the rusting of iron, which takes years to happen. And then we have seen the inversion of sugar and the hydrolysis of starch, which happens in a moderate speed. Neither very fast as our ionic reaction, neither very slow as our rusting reaction. So all these reactions you have seen, these examples, they are having they are heading at a different speed. Now to quantify that speed, we have our rate of reaction. So if you consider the definition of rate of reaction, the speed of a rate of reaction can be defined as the change in concentration of reactant or product in unit time. So this thing should be noticed, that a rate of reaction can be expressed both in terms of reactants or in products. So it is basically the change in concentration of reactant or product per unit time. Now, one more very important thing. So when we see the graph, we will observe this again there, that the rate of decrease in concentration of any of the reactant, so that is called as rate of reaction, and the rate of increasing concentration of one of the product is called as also rate of reaction. So here you can see that we can identify, or you can say calculate this rate of reaction both in terms of reactants and products. So its unit is mole per liter per second. How is it so? So what we are seeing till now, that we are considering the change in concentration with respect to time. Okay, so it is basically concentration time inverse. So concentration multiplied by time inverse, that is change in concentration per unit time. Now what is the unit of concentration that we should consider? It will depend upon the reaction, most probably the state of reaction, what kind of states are we using. So it will be dominated by those you can say factors. Okay, Now, if we are simply doing this reaction and the medium is solution, then we often take the molarity, that is mole per liter. So for concentration, we take this mole per liter, right? And for time, we take it as seconds. So overall, the unit we get is that mole per liter per second. So this is the case of say solid dissolves in liquid, then you would often use that. Thus, unit of mole per liter per second. Change in concentration per unit time. So this is the concentration per unit time. Is this clear? Now, if you move to this gaseous reaction, the play changes here. Why? Because in gases, we are much more interested in the pressure rather than their concentration. So what did I say right now? That we are rather interested in the pressure rather than their concentration or say their volume or anything. Because these things are very easily, you can say, very easily changed by applying more pressure and all that. So they're basically a kind of not that much appropriate to denote it using molarity in all this concentration term. So what do we use is we use this pressure. So the unit in this case is atm per second. So atm is symbolizing your concentration, because the more is the concentration, the more is the pressure. So they are kind of same, right? So it is concentration per unit time. Here again, per second is representing the time inverse. So if I put it in a nutshell, this slide, so we can say that the rate of reaction is variant. It is variable for a various type of reaction, starting from ionic reaction to your inversion of sugar, and in the middle is the inversion of sugar, and at the last is the rusting of iron, which takes a long time. And the rate of reaction can be expressed both in the terms of reactants and products, and its unit is mole per liter per second. Mole per liter per second. And if we are considering gas, then we would see that we would consider atm per second rather than this mole per second. So it will depend upon the question, but for now consider that, okay, we are taking concentration in time inverse, and here the concentration is expressed using your pressure, and here the concentration is expressed using a mole per liter, and the unit of time is same. It's per second and per second for both. So this is for rate of reaction. Now next, so this is how we can justify our rate of reaction, or you can say quantify our rate of reaction. So what do? We consider a hypothetical equation, chemical equation, in which reactant is going to your product side. Reactant is going to your product side. Now what will happen? The 1 mole of the reactant R produces 1 mole of this reactant P. So it is quite clear from this reaction that the stoichiometric coefficient is 1 for both the reactants and the products. So if R1, Rp1 are the concentration of R and P respectively, and T1, T2, and at time T1 we have the concentration as R1 and P1, and at time T2 we have the concentration of R2 and P2. So is this clear? So what we are doing is we are taking a time T1 and we are seeing that the concentration of reactants and product is 1 and 1 for both of these. Similarly, we are taking a time of 2. So at this time T2, the concentration is R2, concentration at time 2, and product concentration at time 2. Is this clear? Right. And one more thing, that we are reacting 1 mole of R to give 1 mole of P. So with these things in mind, we can say that the change in time can be represented by T2 minus T1. Here we are assuming that T2 is greater than T1. Then in that case, we can say that the change in time will be final minus initial. Right. Now, if I consider about the reactant concentration change, then it will be also R2 minus R1. Then it would be also R2 minus R1. This will be concentration change. Next, if we see the change in concentration of product, then it would give us P2 minus P1. That is delta P is equals to, or change in concentration is equals to concentration of product at time T2 minus concentration of product at time T1. Now the thing that is to be kept in mind throughout this chapter is that the square brackets we are using back and forth. So like this one, this is square brackets. Whenever a reacting species is put between the square bracket, it means that we are talking about the reacting species concentration. This is clear? So this square brackets represent the concentration terminology. Now let us define some of the rate of appearance or disappearance. So if I talk about the rate of disappearance of R, then it would be given by decrease in concentration of R by time taken. So that would give us delta R by delta T with a minus sign. So I will tell you why this negative sign is present here. But for now, what is the rate of disappearance of R? It is the change in concentration with the time taken. So what is the change in concentration? Very easy to see that it is final concentration minus initial concentration. R2 minus R1, which will give us delta R. So this thing. And this is happening between time T1 and T2. So T2 minus T1 gives us delta T. So this would be our rate of disappearance of R. Again, if we write in terms of product, we will write it as increasing concentration of P. So it is very clear. So just think of it that reactant will be disappearing. So we will calculate the decrease in concentration of R by subtracting final minus initial. And if you are doing it for product, then it will result in increase in concentration of product by time taken. That is delta P by delta T. Now these both are opposite sides. What is the logic behind it? So if you consider physics or any other rate, the rate should be always positive. Rate cannot be negative. Neither you can have negative distance, nor you can have negative time. For that reason, what will happen? That we will not have any negative rate of reaction. So to keep this rate of reaction positive, what do? That we put a negative sign here, right here. Why are we doing this? The question, right? Why are we doing this? So just think of it. So since it's the reactant, its concentration will decrease with time. So the final concentration will be less than the initial concentration. So if we calculate the decrease in concentration of R, that is final minus initial, then this delta R will give me a negative value. And also time is positive. So negative positive, I will end up getting a negative rate of reaction, and that is not acceptable. So to maintain the sign convention of the rate of reaction, so that it should be always positive as rate cannot be negative, so we put a negative sign. So every time we get a rate of disappearance negative, it is neutralized by the negative sign that is put before this formula. If we talk in terms of product, then it is increase in concentration of P by T. So I have told you right now, but here the product is being formed. So its final concentration will be more than the initial one divided by total time. Therefore, final minus initial would give you a positive value. Therefore, the rate of appearance of P will be positive. So this is the rate of appearance of P. So we have to consider a negative sign along with this rate of disappearance of R, so that the rate of reaction can be always positive. Now moving on to the next slide. So this is the slide that consists of examples of rate of reaction. So we will see kind of three rates of example of rate of reaction, and we'll see something very important during this rate of reaction. So the first reaction that we're considering is our conversion of Hg plus Hg reacting with Cl2, giving us HgCl2. Now, if you want, one thing you should remember that each of these have a coefficient of 1. So keep this thing in mind. It will be cleared in your next slide. So if you want to write the rate of reaction for this, then how you'll write it? In terms of reactant. So in terms of reactant, I have told you that change in concentration of reactant by time with a negative sign. So mercury is changing its concentration first of all. So it is the reactant. So we will write change in concentration of mercury divided by the time through which it has transversed to change the concentration. and it is put along with a negative sign, right? So it is put along with a negative sign to maintain the sign concentration or sign convention. Then we have one more reactant, that is Cl2. Now I will ask that it is gas, why did not we consider the pressure rather than the concentration? So I would suggest that, okay, sometimes it is convenient to use the pressure, but most of the time of this chapter you will see the concentration term. So majority of the time you will be seeing this concentration term rather than the pressure term. For some reactions, or you can say some derivation, we would invoke those things, but for now just consider the concentration. So how will write it? Change in concentration of reactant divided by the time that it has used to do this change, followed by a negative sign, so that the sign convention is maintained. So this was for reactants. This both are for reactants. For product, we have change in concentration of product with respect to time, and we do not have any negative sign or something like that in the front of this say fraction. Why? Because product concentration is increasing, so final minus initial would give me positive, and time can never be negative. Hence we will give the final sign as positive along with this, so that the rate of reaction can be maintained positive. So rate of disappearance of any of the reactant is same as the rate of appearance of the product. In which case, in cases where we have this stoichiometric coefficient 1, then in that case we can say that, okay, the rate of appearance of any of the reactant, it's same as the rate of disappearance of the reactant. So opposite of that, rate of appearance of this product is equal to the rate of disappearance of the reactant. So this is the thing about first example. Now if you see the second example, this is more important to look upon. So for expressing the rate of such a reaction where the stoichiometric coefficient of reactants and products are not equals to 1. So here you can see it is not equals to 1. This one is also not equals to 1. Okay, so this, for this case, the rate of disappearance of the reactant or the rate of appearance of the product is divided by the respective stoichiometric coefficient. So first you have to understand what is this rate of appearance. So I've mentioned this earlier also. So if I write it more appropriately, rate of appearance of product for these reactions. Suppose I'm writing for this reaction 2HI, we are getting it from H2 and I2. Suppose we are writing the rate of appearance of product, then it would, the product here are delta H2 and divided by del dt. Okay, so this thing is clear, right? Then this is the rate of appearance of product, rate of, so one more product is there, delta I2 by dt. Now rate of disappearance of reactant. So it would be simply change in concentration of HI divided by dt, del T, without any stoichiometric coefficient. So this is the thing. Now if you divide it with the stoichiometric coefficient as we have done here, so we have divided this rate of disappearance of this delta HI by del T along with this negative sign is the rate of disappearance. We have divided by the stoichiometric coefficient. Then in that case, we will get the rate of reaction. So if the stoichiometric coefficient is 1, then the rate of appearance of the disappearance will be equal to the rate of reaction. But if the stoichiometric coefficient is not equals to 1, then the rate of appearance or disappearance of this reactants or products will be not equal to the rate of reaction. That is why we are dividing to make all these things equal, we are dividing it by 2 to get the rate of reaction. So is this clear to all of you? So this is our second example. Similarly, we can think of another example where we have multiple reactants and multiple products. So we have 5 Br minus reacting with BrO3 minus 6H plus 3Br2 3H2O. So there are 6 species involved in this, 3 reactants and 3 products. Now if I ask you to write in terms of all of these, so how we'll write? So first we'll write it for Br minus. So rate of disappearance of Br minus will be delta Br minus by delta T minus with a negative sign. Then we will divide it with the stoichiometric coefficient, that is 5, so 1 by 5. So rate of disappearance will be minus delta Br minus by delta T, and the rate of reaction will be just 1 by 5 of those. Moving on to the next reactant, BrO3 minus. So what is the rate of disappearance of BrO3 minus? It is minus delta BrO3 minus by delta T. Now since the stoichiometric coefficient is 1, so the rate of disappearance of this species will be equal to the rate of reaction. So no need for division by any number or any integer. Not integer, we can say real number. That would be more appropriate because sometimes the stoichiometric coefficient are fractions also. Then moving on to the next species, that is H plus. So change in concentration of H plus divided by change in concentration of time along with a negative sign would give you a rate of disappearance of this H plus. Now if I divide again with the stoichiometric coefficient, so it is 6 here. So I am dividing it by 1 by 6 to get the rate of reaction. So these all are becoming equal. You can see that this all are becoming equal, and it is quite obvious also because the rate of reaction will be same. Either we consider in terms of products or we consider in terms of reactants. Moving on to the next product. So the rate of appearance of this Br2 with a positive sign because it is product, when it is divided by 1 by 3 we get our rate. And similarly, if we consider the rate of appearance of water along with time, with change of time, divide by 1 by 3, we will get it as the rate of reaction. So you can see how beautifully we have say described the rate of reaction using the reactants and the products. But the thing that you should keep in mind that you should have a balanced chemical equation. So suppose this equation was not balanced and we do not have this stoichiometric coefficient. This would be 1. Suppose it is 1, no problem. It is 1, it is 1. Then you should not do it for this kind of reaction. So first you should notice that whether that reaction is balanced or not. Then only you can use this methodology to find the rate of reaction. Now if you see this gaseous reactions, so the gaseous reaction at constant temperature and is directly proportional to the partial pressure of the species, right? So in that case, what we can do, let's suppose for the previous reaction we've seen that, or again if we take this reaction like N2 plus H2 NH3 2 3H2. So if all of these are gaseous, then we can write that change in pressure. So let me do it on a different page for you more clearly. N2 gaseous, H2 gaseous. It is giving me NH3. First of all, we will balance it, multiplied by 2, multiplied by 3. Keep it as it is. Now, if you write here the rate of reaction for this, suppose all of these are gases. Suppose we are doing it in the term of pressure. Then what we will write? Change in pressure of N2 with respect to time t, and coefficient is 1, so it will remain 1 with a negative sign. Again, change in pressure of H2 with respect to time t, and that will divide by 1 by 3 along with a negative sign. This will be equals to 1 by 2 change in pressure of NH3 divided by delta T. So 1 by 2 is the coefficient, and we have a positive sign since we are dealing with the product. So here you can observe that we are say describing our rate of reaction in terms of the pressure rather than the concentration. So for gases you can do this also, right? Now moving on to the last topic for today, that is the average and instantaneous rate of reaction. So let us see, very interesting topic to consider. So let us start with, if we are seeing the reactant, right? So let us consider the reactant part. Now what is average rate of reaction? What is instantaneous rate of reaction? So for average rate of reaction, we see the change of concentration for a longer period of time. Okay. And for the instantaneous rate of reaction, we see the change for a slight point. So what is the slight point? What do you mean by this? So suppose this is a concentration of reactant. So you know that as the reaction proceed, the slope will go down, 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 and will ultimately become parallel to this. Is this clear? Right. Now, if you see the average rate of reaction, then we will consider a large time interval, that is delta T. So we are going from T1 to T2. So if you write the average rate of reaction for this interval, then it would be initial concentration, that is R1, and final concentration at R2. So it will be R2 minus R1, that is written as delta R, divided by delta time T along with a negative sign. So this would give you average rate of reaction, that is R2 minus R1 by T2 minus T1. Now if you are asked that what is the instantaneous rate of reaction, so what do we do for this? So instantaneous rate of reaction is considered at a time T. Suppose you are told that what is the rate of reaction at a time T is equals to 3 seconds. Then what you will do? So what we will do is that, suppose this is your required time at which you have to calculate. So you will simply draw a tangent at that point. What we will do? We will draw a tangent at that point and we will try to calculate the slope of it. And whatever would be the slope, the negative sign along with that would give you the instantaneous rate of reaction. So is this clear? So what I am saying here is that the instantaneous rate of reaction is the slope of the tangent at that point at which we have to calculate the rate of reaction along with a negative sign. Because this slope, you can see, this slope is negative. This slope is negative. So it would give you a negative rate of reaction. So to just, you can say, compensate it. So we have seen it earlier also that we have to keep the sign positive. We put a negative sign with against the slope. Now one more thing is to be noticed here. What is it? So the thing is that the rate of reaction, or you can say, is decreasing with respect to time, or the rate of formation of this reactant, this disappearance of reactant is decreasing with time. How is it so? How can you observe it? So let me do it for you. Suppose we find the rate of reaction at 3 instant. Here we use a different pen so that can be more visible. Here, and here. Now if you draw a tangent at each of these points, the first would be appearing like this. Second one is already done, and the third one will look like this. Now if you see the steepness, slope is the steepness only. So you should have this idea. The slope is nothing but the steepness of this line. So you can see this, it is more steeper. This is moderately steeper, and this is the least steeper of all of this. So you can see that the rate of reaction is slowly decreasing with respect to time. Yeah, it is a direct influence of your Lee-Chatterjee principle that says that if you change a reaction in such a way, then the change would be compensated by moving the reaction in the opposite direction. So kind of slowing the reaction is a direct result of this Lee-Chatterjee principle. So you must remember this, that the rate of reaction is changing with respect to time. And how you can imagine it? Just look at the graph. You will get a clear picture of it, that how this rate of reaction is diminishing with time. Okay. So you should, have you got the point of what is average and instantaneous rate? Now if you want, you can do it same for the product also. So the product concentration is rising with time. So if you want to calculate the instantaneous rate of reaction at this point, so it would be dp by dt is equals to slope. Okay. And for the average rate of reaction, it will be delta P by delta T. That's P2 minus P1 by T2 minus T1. Here also for instantaneous, what we have done, so suppose you have to calculate it at this point. So we have just drawn a tangent here. And then what we have done, the next part, that we have calculated the slope of it. Here is the slope of it, so that we can get the instantaneous rate of reaction along with a positive sign. So this is the difference between average and instantaneous rate of reaction. Now, if you are asked that which one is more, you can say which one is more useful. So I would suggest that, and how I am suggesting based on the recent times, or you can say experiments and all. So if you are conducting experiment, then you will see that this instantaneous rate of reaction is of much more importance rather than your average rate of reaction. So you will see it how. So while calculating the order of reaction, you will see that how this instantaneous rate of reaction is used from time to time rather than your average rate of reaction. For those who have studied must have seen this also. So no problem if you have not studied. You will see that at this point of time, the rate of reaction is this. At this point of time, the rate of reaction is this. And you have to use the data to calculate the rate of reaction and then the order of reaction. So you can say that this instantaneous rate of reaction is much more handy in doing, or you can say measuring the slowness or speediness of a reaction. So is this clear too? So the instantaneous rate of reaction is much more useful than your average rate of reaction. So what we have studied today is what is the rate of reaction and how this chemical kinetics is dealing with it. So the most important formula or the note that I want you to keep in your mind and keep it for the further chapters of this lecture is that, suppose we have a hypothetical reaction like this, Na going to Nb, then the rate of reaction would be written as one by n, suppose it is m. Okay, this is m. 1 by n delta A by delta T along with a negative sign is equals to 1 by m delta B by delta T along with a positive sign. So this is a takeaway note for you. So this formula is important. Questions are asked from here. So thank you for today's class. With this, I end my lecture.